I will start shortly. Let's give it one more minute and we'll start. I guess we can give a couple of more minutes. Okay, we'll get started. So let me give you a little bit introduction about Data Cabinet. Data Cabinet is a cloud-based programming platform where you can keep your Jupyter notebooks and programming environments, and you can easily share with your peers. And we are trying to build more and more deep learning features into it. So, so in today's, so we are using Data Cabinet today to present this topic of regularization, which is based on Ian Goodfellow's book. And so let me get started, and then I can also show you some other notebooks with code samples. And so we are using the presentation feature of NB Grader to do this. So at a higher level, how do we think about machine learning problems? So we are given some data, like for example, we are given age, height, and education of a person, and the income of the person. Suppose we are given like some data around this. Can we make a classifier that given any age, height, and education can give us the income. So this is a typical machine learning problem. So the way we model it is y is equal to fx plus epsilon, where y is the income, fx is the effect of age, height, and education that we are trying to model, and epsilon is an irreducible error, which can be impacted by factors that are not related to age, height, and education, which could be like, for example, geographic location, which could affect income. And so another way to think about it is like a probability distribution. So let's suppose we were given the probability distribution of age, height, education, and income. Then we could then these data points that are given to us could just be samples from this probability distribution. So but generally we are not given the probability distribution in real life. We are only given data points. So in machine learning, we are trying to model this probability distribution, and sometimes we assume a probability distribution to be able to intuitively understand some of the machine learning results. So let's understand. So this lecture is for regularization, which means how do we, given test data, how do we given some test points, how do we make sure that our classifier works, or given some training points, how do we make sure our classifier works well in the real world, like given some test points. So we'll start with some basics. So let me see if there are any questions. Okay. So one measure. How do we determine how good the classifier is doing on test data? So one measure could be that we get we get a test set, test data, and we get a mean square error. We apply our model on each of the points on the test data. We get corresponding y's for the test data, and we know the actual y's, so we can subtract them and see how much the difference is, and we can do a squared error, sum of squared error as well. So that could be a measure of how well our classifier is performing. But when we get we can also try like a number of different models and pick the one which gives the least error in those classifiers. And this is the idea behind cross validation and a lot of other techniques. But how do we generate these different models that we test that we apply the test data to and figure out which one is the best? So one way could be that you take you increase the flexibility of the classifier, which means in a way intuitively you could think of it as like a less flexible classifier is a linear classifier. So this yellow line, if you see here, is a linear classifier, which is not a very flexible classifier. But if you make like a second degree classifier, then it's a little more flexible. Yeah, and then there is like a 16 degree polynomial if you're trying to fit it. That can be very flexible. So let's suppose what we do is we increase the flexibility of the classifier and try to figure out what the test error and the training error are. So this is a good example in which we simulate the points. So we basically take a probability distribution, we generate some points from it, and then we start fitting multiple models, starting from less flexibility to more flexibility. So if you see the first degree or second degree model, or it's not a degree necessarily, it could be something else as well, but a model with the flexibility of 2 is underfitting because the mean squared error is very high on the test set as well as the training set. But as we increase, the mean squared error on the test set keeps coming down as we increase flexibility. And so this is the optimum point, around 6. But as we keep going further in flexibility, the least square error in mean squared error in flexibility comes down. Mean square error on training set keeps coming down because it will always try to figure out the training set. But the mean squared error on the test set starts going up. So this is a very typical, this U shape is a very typical shape in machine learning, where things go good for a while, and then the error starts going up. So let's go and see the origin of this. So bias variance trade-off. This is a very celebrated result in machine learning, and so the idea is that if you take a set sample data point, if you take some training data, you sample it, you sample a subset of the data, and then you fit one classifier onto it, and then you take another sample and you fit the same classifier on it, and then you make a number of different classifiers which are the same classifiers. So if it's linear regression, then it's linear regression for all of these subset of data points, but you will get many different classifiers. So if you take a new test point and you try to find the expected value of the test point's error with respect to all the different classifiers that were formed, then it is equal to the variance of the classifiers. I should call I should call it fx, not x naught. It's equal to the variance of the classifier of all the classifiers at point x naught. So at x naught, there will be a lot of values given by all these different models, and then the variance of that plus the bias of fx naught. So the bias, how far is it from the actual y naught? So all the different y values that were predicted by all these different models, how far is it from y naught? The square of that, and the variance of the irreducible error together form the actual mean squared error. So this, if we put this result in the context of increasing flexibility, then we can see on the left hand side that as the flexibility increases, what happens is, and on every point we are fitting like many different models of the same flexibility, and then measuring the bias and the variance. So if you see this, as we increase flexibility, this blue line, which is the line of the bias, keeps coming down, but the orange line, which is the line of the variance, keeps going up. So as we increase flexibility, variance goes up and bias comes down. But the sum of the bias and the variance, which is what we are interested in, which is the root mean square error of the test data, comes down for a little bit and then starts going up. So in this case, the optimal value is around 6. In this case, the optimal value is around 3. And in this case, the optimal value is around 10. Where, in this case, you could argue that it's a very so there is a lot of variance in the data, so it needs the actual. So it also depicts how the actual probability distribution is. So it kind of says that the actual probability distribution is that generated the data is around the flexibility of 10, or the actual probability distribution that generated the data is around the flexibility of 3 in this second one. So that's the let me see. If there are any questions. Oh, none. Okay. All right, so let's go to regularization. So what happens in regularization? Now, in regularization, what we are trying to do is we are trying to find this optimal point. So what we do is we generally take like a very high bias, high capacity or high flexibility model, and then we apply regularization to reduce the generalization error. So what we do is we try to reduce the bias, we reduce the variance by using regularization, so that starting from a very high flexibility model, we come down to like a model that has very good test error. So and in regularization, we also try to, there are various ways to do it, but we always try to figure out some prior information that we have. We try to encode that in our learning in such a way that we can find this point. So it could be different for different strategies. So we'll come across different strategies, but it could range from dropout to early stopping to L2 regularization to L1 regularization. We have a lot of different strategies to find that optimal point. And so here there are two listed, which is adding a restriction on the parameter value. So for example, something like this parameter value cannot go over k, or adding an extra term in the objective function. So for example, we are trying to minimize the objective function. So we put like a square of all the coefficients on the objective function. So this can lead to better test case performance. So there are multiple techniques, but the common theme is that we know something in the beginning that we use to get the best result. In neural networks, of course, neural networks have very high capacity, so regularization brings down the variance of the model. So let me show you a coding example of bias variance. So in this one, so I'll just go through it quickly. And so this one, what we do is we take a sine curve and we add a normal to it. So here we are assuming that we are given the probability distribution. So we are taking the sine curve, adding a bunch of normal noise to it. That's our initial probability distribution, and we are sampling a bunch of points from it. So now in this one, what we are doing is we are fitting a 8-degree polynomial and trying to estimate this sine plus noise distribution that we have. So this is how it looks like. A 8-degree polynomial will optimize it, will fit it something like this. Now what we do is we take a 4-degree polynomial, but we sample different subsets and we fit different different models onto it. So if you see, there are a bunch of different models and a bunch of different models that estimate the sine curve. Now what we do is we go and do the actual, we increase the flexibility and we fit a number of models for each flexibility, and we figure out the bias and variance for the models, and then we plot this bias and variance. So if you see, around degree 5 we get the best point. Before that the error is reducing, but after that the error is increasing. So a polynomial degree 5 is best for approximating something like some sine curve like this. So so this is the idea behind bias variance trade-off. So let's go to let's see if there are any questions. No. So parameter non-penalties. So non-penalties are one way to do regularization. So by non-penalties, we mean so norm of a vector is basically the length of the vector. So it's always positive. And so we add if you see the weights as a vector, then they will have a length. And we want to make sure that that length, if it's too much, then we add a penalty. So that's what is called a non-penalty. And so we could write it. So we could take the non-penalty as sigma of theta, where theta and w are the same things, weights. Theta is just weights. And we also take a hyperparameter alpha, and we add alpha and then the norm penalty. So the norm penalty could be norm multiplied by 2. It could be norm just norm squared or norm cubed, anything. But this, we are trying to add this term to the original cost function and try to reduce the value. So it has the effect of irregularization, because we are now also trying to put another restriction on the theta or w. And so different forms of norm, whether it be L1 norm, L2 norm, have different characteristics. So for example, if you just add the absolute value of the of all w's, and then take that as a norm, then it's then it leads to feature selection, which means some it will prefer some features which have a large say in the output versus others. So it will do some it will have different properties. And just to note, for neural nets, weights are regularized, but biases are not generally regularized, because biases do not lead to so much variance. And if you try to regularize biases, then the model capacity becomes too low, and it leads to underfitting. And also in neural networks, for every layer you could have a different alpha, this alpha hyperparameter, or you could have the same alpha for every layer. Okay, so L2 regularization. So L2 regularization going forward, some properties of L2 regularization. So if you see, L2 regularization can also be written as this term, which is alpha divided by 2 multiplied by the square of all w's. So now, if you take the gradient, so the gradient of this cost function, then this is the gradient of the original cost function, and this gets added to it, alpha multiplied by w. And now if you take a single gradient step in w, then this is w minus epsilon into this gradient. So if you see, if you rearrange this is almost, this is okay. So this is almost the same as the original. This is almost the same as the original equation, just that there is a w on every step gets reduced by epsilon alpha w. So on every step there is a slight change, but that doesn't tell us too much. We need to find out what happens at the end. Like if every step you reduce w by epsilon alpha w, then what happens at the end of it? So we'll make some. So over the course of training, what happens? And so let's see if there are. Okay. So let's do. So we will make some. So to analyze this, we'll make some simplification. So one simplification is that we are assuming that the cost function itself is just quadratic in W, and so that way we can say, like for example in linear regression, we have a quadratic cost function. So So for any point, J bar W is, and let's suppose W star is the minimum point, like where the minimum cost function occurs. And we do J bar W is equal to J bar W star plus half multiplied by, so if you do a Taylor series expansion, so this is the minimum point, and the first order derivative at the minimum point is 0. So there is no second order, first order. The second order term is this, and there is no third order because we are assuming that the cost function is quadratic. So the second order term will look something like this. This is half multiplied by W minus W star uh, multiplied by the Hessian, which is the second order matrix, multiplied by the same W minus W star. Now, there's one good thing about this, that every term, this term is this term is a scalar, right? And this scalar is always this. Wait, this is a scalar. W minus W star. Yeah, this is a scalar, and this scalar is always positive for any W, because W star is the minimum point. So J cannot go below W star. J cannot go below JW star. So this term has to be always positive. So this is the definition of a positive semi-definite matrix. So H is a positive semi-definite matrix with multiple with all positive eigenvalues. And so now so given this term, if we try to figure out the derivative of JW, then it's just HW minus W star. Now to get so in this case, you can see that the minimum happens at W star, because if you equate this to 0, then W is equal to W star gives you the minimum point. But what happens if you add a alpha W to it? So if you have a regularization term, then this derivative term will become HW minus W star plus alpha W. So now if you rearrange this, and H is a positive semi-definite matrix, so you can write it as a Q delta Q transpose, where delta is the matrix, is the diagonal matrix of eigenvalues, yes, which are all positive. And now if you rearrange this, then you will get something like this. This is the equation for the optimal weight. If you solve this equation and substitute H with Q delta Q transpose. Now the thing is, if you put alpha is equal to 0, then all these terms cancel out and it becomes W star. But if you put alpha I, then what happens is, you can think of it as this way. W Q transpose takes it to the coordinates of the eigenvectors. Then this term actually intuitively, this term actually expands and these are both, if you see, these are both diagonal matrices. So what these do is they stretch each component in the eigen coordinates by a lambda I divided by lambda I plus alpha, which is lambda I is the ith eigenvalue, and then it brings it back to the regular coordinate space. This Q brings it back. So you can think of it this way. And if you look at this value, lambda I divided by lambda I plus alpha. So so if the lambda I is too small, then it gets affected too much. So if lambda is 0.1 and alpha is 10, then it's almost 0. But if lambda is 10 and alpha is 10, then it doesn't get affected by this transformation that much. So it squishes the slower eigenvalues by more than the larger eigenvalues. So this is another way to look at it. So let's see if the unregularized cost function is this upper contours, the solid contours, and W star is the optimum point. These contours are the equal value points. Now these dashed contours are the contours for the regularization function. So now W star, if you see, has almost equal W1 and W2. But if you see in W2 direction, the gradient is going fast, is more than W1 direction, because it's going, the contours are moving faster. Now you can also say that the Hessian has a higher eigenvalue in this direction. So we will, and let's suppose W bar is the point where the optimum occurs when we add the regularization function with the cost function. Now, if you see, W bar has squished the W1 coordinates much more than it has squished the W2 coordinates, and you can see that W2 had a higher eigenvalue because it has a greater gradient. So that's the so let's do a similar analysis for L1 regularization. So we'll do, let's see. Okay, for L1 regularization, we are actually adding the sum of the absolute values of WIs. And there is also a hyperparameter alpha, which controls the strength of regularization, similar to L2 regularization. And if you see, the derivative of the regularization, it is the original derivative of the original cost function plus alpha multiplied by sine of W. But here, if you do take a quadratic loss and try to do that analysis that we did for L2 regularization, then we'll also have to assume that the Hessian is a diagonal matrix, which can be done if all the input features are not correlated. So all the W's are not correlated. Yeah, and so we get this result. The result is we get this result where we do JW is JW star, which is the minimum point, plus half multiplied by HII multiplied by WI minus WI star, the whole square, plus alpha WI. So this is the, for any W, if we try to figure out what the value will be, and under these circumstances, it will be something like this. Now, if we do analytical solution to this by taking the derivative, we will get the optimum W is the sine of WI star multiplied by max of 0 or WI star minus alpha divided by HII. So the way this works is that when WI star is less than alpha divided by HII, then the value is 0. But if it's greater, then it gets shifted by that much. So this leads to, like, a lot of the weights which are smaller get shrunk to 0, and the rest get shifted by a little bit. So this leads to a different form of regularization. So you could also think of it in a different way. So let's suppose L1 regularization contours are square. If you can see, the equal valued points lie on a square, but the equal valued points for L2 regularization lie on a circle. And let's suppose these are contours for equal contours for beta, for the original cost function. So you can intuitively see that this original cost function will hit this. So one thing is that it will. So if you, for example, this point, which is where the larger contour in the left figure meets the y-axis, is the optimal point, then it will be the sum of this regularization value plus the cost function for this contour, the larger contour. So it will always hit on a corner. It will never hit in the middle, because if it hit in the middle, then we can always take a different contour which hits in the corner, and the total value will be reduced. Total value of the cost function will be reduced. So the cost function is the sum of this contour plus this contour. So it has to hit on a corner, at least in the square case. But if it's a circle, which is L2 regularization contours, then it will hit somewhere in the middle, because it need not, because circle is shaped that way. So you can also see that circle L2 regularization does not lead to feature selection. Here, only the beta 2 feature was selected. The beta 1 feature was put to 0. So that's the idea behind L2 regularization. So now let's come to non-penalties. Thinking of non-penalties as a constrained optimization. So we can think of, so constrained optimization is a technique where we try to optimize a function by adding a set of penalties, and each penalty consists of a coefficient and a function representing the constraint, one constraint. So for example, we can add a penalty something like this, where alpha is a coefficient and this is the constraint, that theta alpha has to be less than k. If it's greater than k, then there will be a positive penalty, otherwise there will be negative penalty. So now we can this becomes a generalized Lagrange function, and we can optimize it. And you can think of it as if sigma theta is greater than k, then we are trying to pull it down. The optimizer is trying to pull it down, as well as put j down simultaneously. So if you, and this can also be optimized using SGD for a fixed k and theta alpha. Like we can find the theta and alpha using SGD, and if we fix k and theta in this equation, then it also becomes similar to minimizing this sigma theta plus j. So if you see this one, if theta is a L2 if sigma is a L2 penalty, then this is the same as L1 or L2 regularization. In fact, L2 and L1 regularization, you could find a corresponding k. So you could find, it could also be thought of, L2 or L1 regularization could also be thought of finding a k and constraining theta L1 or L2 to within that k. So so in a way, non-penalties are trying to constrain parameters, the L2 or L1 norm of the parameters, to within a particular k. And sometimes we can even find that k. So that's non-penalties as constraint optimization. So how can we make use of this these constraints? So instead of adding non-penalties, what we do is, every time we do a SGD step, we reproject thetas to satisfy this constraint. So if thetas go, and if we do a SGD step on the original cost function, so we don't apply any norm, and every step what we do is we reproject theta, so it becomes less than it satisfies this sigma theta minus k properties. So so this process can have a number of advantages. One is that if you already have a idea of k, then this can be used. And non-penalties generally make the original problem more convex and harder to train and easier to get stuck in a local minimum. So if we do this, then it will train more smoothly. Or it can also lead to without norm. Yeah, but we have to keep in mind that without non-penalties, if we are using very large learning rates, then the gradient, if the gradient is large, then it can lead to numerical errors very fast. Like on every step, it will get multiplied by something, some big number, and it will lead to a numerical error very fast. Okay, so regularization for underdetermined problems. So let's suppose you are given a data set of only 5 points, um, like 5 people who have some disease, and you have a gene, a genetic sequence of 2,000 characters, and so there could potentially be 2,000 features, but you have only five data points. And so this is an underdetermined problems. You can take like any more than 5 features, and you can fit the 5 points very easily. So how do we determine, how can we use regularization on this problem? So what we do is we basically add a regularization term. So you can also think of it as, if you're adding a constraint, then you are adding that all L2 norms should sum up to less than 10. And now if you fit like a logistic regression or a linear regression to this problem, then you could find a real solution to this problem. So the regularization could also be used for underdetermined problems to make it determined. And sometimes it also gets used. You can use regularization to, if you are given a singular matrix, and a lot of times machine learning, it's all about changing the fact, inverting the matrix. So you can add like a regularization term to make it invertible. Okay, so let's go back. Okay, so data augmentation. So data augmentation is, so of course, if we are given a larger data set, then our machine learning model will do better. Uh, but how do you generate these data sets? So generating a lot of data could be harder. But in certain domains, it's easier to generate a lot of more data by tweaking the original data. So, for example, images. If there is an image of a cat, if we translate it 10 pixels to the right, it will still be a cat, and if we rotate it, it will still be a cat. So we can do these augmentations to the data set, and we can get more data. And this we have to make sure that the translation, like rotating a D becomes a B and it changes the class of the data, that should not happen, but otherwise it's a good technique. Speech recognition can also work with dataset augmentation. And we can also apply, sometimes data augmentation can take the form of introducing noise. So we can introduce a noise to the input and hidden layers, just to make sure that our classifier is more resilient to noise. And some things to note are that data augmentation should be kept in mind before comparing algorithms. If you have one algorithm that you train with one set of data, and then if you have another algorithm that you train with augmented set of data, and the augmented one performs better, then it's not necessarily necessary that the augmented one is actually a better classifier than the initial one. It just got some better data. And Also, that some algorithms can be seen as themselves introducing some Gaussian noise into the data. So how can that be called data augmentation? Data augmentation generally refers to like using the domain specific techniques. So in image or speech, we have domain specific techniques to augment data, and those are called data augmentation, and not like add like some something that could be considered part of the machine learning process itself. So let's go to the next slide. So there could also be noise robustness for weights. So noise robustness for weights means that instead of introducing noise to the input, the activations of hidden units and input units, what we do is we introduce noise to the weights itself. So whatever weights we have learned so far, we are introducing some noise into it. And our cost function generally is, let's suppose our cost function is this, given find the expected value of the model output versus the actual output, the whole square, which is the mean squared error. And if we inject a small amount of error in weights, then the model output becomes this term. And if we are trying to figure out the expected value of the classifier with small error in weights, then it becomes similar to minimizing the actual cost function, but with a regularization term of, yeah, and we are assuming that these noise terms are all decorrelated from each other, and have a and have a mean of nu. Then it's like using the original cost function with a regularization term, which is the expected value of the square of the gradient of x with respect to of the output with respect to w. Now, norm of the gradient, of course. So this can be also thought of as that we are constraining the norm of the gradient. By doing that, we are making sure that the gradient is low, and w. So changing w by a little bit does not change the output by much. So we can get like a robust, we can get a more robust classifier that way, which does not change with w that much. Okay, so label smoothing. So so this is where the previous class ended, and we will start with. So let's give it like 5 minutes, and we'll get started with the next class. I will be right back. If you have any questions, please. Okay, so we'll get started with noise robustness for outputs, label smoothing in a little bit. All right. Okay. Okay, we'll start with label smoothing now. So if our output has some error, and we know that the outputs are not labeled properly, then we can model that as as a as a regularization called label smoothing. So we can assume that um, there is a there is a possibility epsilon that there is an error. Then all other labels are so when we do like softmax, then what we assume that one of the classes has probability one, given the test data, and others have a probability of 0. But here we'll not assume that. Instead, we'll assume that the one of them is a probability of epsilon, and the rest have the probability of no, one of them has a probability of 1 minus epsilon, and the rest has a probability of epsilon divided by k minus 1. And if we this is called a label smoothing, and we can train this instead of training the original. Um, so max likelihood on classification using softmax can be hard and hard to learn because it never converges. But we can use like in the previous example, we can use L2 L1 regularization on the weights, but this could lead to more increased bias while we decrease the variance. Label label smoothing the book claims can be a better technique because it does not increase the bias too much. So now semi-supervised learning. So what is semi-supervised learning? So instead of learning py of given x, which we generally do, like given an x, we are trying to
get a probability distribution and we can predict why. We are actually trying to look at the data. We could also do something like we can look at the data itself, see some patterns in the data, and figure out those features, and then actually make the prediction. So this technique is called semi-supervised learning. So we actually first analyze the structure of the data, get some features out, and then we apply the actual machine learning, supervised machine learning techniques on top of that. So that way, and so in in deep learning, uh, we are we are kind of um, in deep learning we can also try to control how much of the generative criterion, which is like the unsupervised finding the features, and some how much of the discriminative model, which is given the features, what is y, what is how much of each can be used, and by choosing appropriate amount of both techniques, we can get the best classifier. So this is called semi-supervised learning. In formal terms, we can see instead of modeling py given x, we can first model px or pxy, which is we can see the points, or we can see the points with or without the output labels, and we can figure out some prior beliefs, and that for example, they cluster around y-axis. Then we can use that belief. We can use that information first, and or we could do some clustering or PCA, and then we can use that information to actually fit the y given x. Okay, semi-supervised learning, then multitask learning. So similarly, in multitask learning, if you are given two tasks instead of one task, like given a set of points, predict the label and predict the color, let's suppose. So then you know that there are some underlying features in the data that are common between the two that explain both, but then they have uh, some extra processing or some extra variations that are specific to each task. So uh, under these circumstances, what we can do is we can have a shared layer, H shared, that acts on X and produces some features, and those features are acted on by H1 and H2 to produce Y1 and Y2. And so this is how multitask learning works. That you actually and it makes it better to learn. And we get more data. And H shared can be better learned under these circumstances than learning them separately. So now there is another technique called early stopping. How many steps do we take? That's a topic that can be used. That's a thing that can be used as a regularizer. So and there is some so there is evidence around it. So first, let's look at this picture. So if you see the training error in blue and the test error, validation set error in green, then it has a very similar U shape that we're used to seeing for all the other hyperparameters. So if you see, as time epochs go by, how training error goes down and how validation set goes up. And so this one, uh, so how do we figure out the optimum point where we should stop? So one way could be that we take our data and we partition it into a test data and training data. We every n steps we are fitting the classifier on training data. Every n steps we do a validation, and we try to figure out the best coefficients that we have seen so far. And if p validations go by and we haven't seen a better coefficient than the last one, then we give up and say that the previous best was the best coefficient that we have seen so far. So this is how early stopping could be used. And so early stopping So early stopping, there are some properties. It can be thought of as a hyperparameter. So the number of epochs that you will go can be thought of as a hyperparameter. Um, but this hyperparameter can be very easily chosen as part of the training itself. And it's unobtrusive, which means that it does not do too much. It does not change our learning too much. It does not change the objective function or the training procedure, whichever you're using. It changes it a little bit, that you have to do validation, but you can do it in parallel. Or the set of allowable parameter values. So, mm, so for example, if you're using weight decay, and if you choose too much weight, if you choose too much, if you choose too much alpha, then it will get then it will get trapped in a bad local minimum. But those things don't happen the with the regularization that happens using early stopping. Uh, and it can of course be used with other regularization techniques. Okay, so how do we early stopping? There is one problem, that we have not seen all the data. We are partitioning the data into test set and training set, but the data that went into test set could also give us some more, could make the neural network better. So what we can do is, we can initialize the model again, and we can find the number of epochs that are the best, and then we initialize the model again, and we train for those many epochs. That's one way to do it. Or what we can do is, but this one is expensive, because you have to do the whole thing again. The other way is to keep to after we have found that, okay, these we are going to stop because we have found the best classifier, best number of epochs to train for. We continue training. We put some more data validation set. We put the validation set into the training set, and we keep training uh, until the error stops below the point where the early stopping happens. So if the best theta was had an error of zero point 0.9 or zero point 0.1, then we will keep training with new data sets until we get another point which has less than zero point 0.1 error. And now we do not have any validation set. Everything is in the training set. Uh, so that's how we use the rest of the data. So early stopping can also be seen as a regularization. So an easy intuition to think about is that if there are tau steps of epsilon each, and the gradient is bounded by max of the gradient, then tau epsilon max of gradient is the constraint region in which the weights lie. So no weights can deviate more than tau epsilon max of gradient from the original weight. So we can see that this is a constraint we are putting on W. So this can be thought of as a regularizer that way. But let's do a more rigorous. If you look at a more rigorous analysis of how uh, how early stopping is related to uh, L2 regularization, and given the same same setup, we have we have a quadratic loss function, and we have a and we are trying to figure out, and W star is the minimum point of it, and Hessian is the double derivative at W star. And so doing the same analysis, that JW is JW star plus first derivative is 0, second derivative is this, third derivative is again 0 because the quadratic cost function has third derivative 0. Then the derivative of this cost function is HW minus W star. And now if we see W at time t is W at time t minus 1 minus epsilon into this multiplied by this derivative. So at every step, we are going in the direction of in this much in the direction of the derivative. So now this can be rewritten as Wt minus W star is I minus epsilon h multiplied by Wt minus 1 minus W star. And now if we and h again is a positive semi-definite matrix, it can be written as q delta q transpose. We now we can write it, we can rewrite this formula a little differently as qt Wt minus W star is equal to I minus epsilon delta qt to Wt minus 1 W star. So so now we can further simplify it so that it becomes qt Wt is, we can remove the Wt minus 1 term from here by doing progressively, by making some assumptions, and by progressively eradicating them, taking W0 is equal to 0, and with some assumptions you can prove that Wt is basically I minus this formula. And now if you see, compare it with the L2 regularization case that we thought of, that we discussed before, that in that one qt W optimal is delta plus alpha I inverse delta qt W star. So if you see that this A and B have a very similar structure, and we can, using these, we can see that using A and B, we can see that for L2 regularization, alpha is related to in this case at least, is related to epsilon tau in this manner. So so this proves our intuition that epsilon tau plays a very similar role to L2 regularization. So the learning rate and the number of steps together constrain the original W's, and they do it in a way very similar to that of what L2 regularization does. So parameter tying and parameter sharing. So in this case, if we are training two classifiers, I think the latex is a little wrong. If we are training two classifiers, and what happens is we know that the outputs are we know that the inputs are the same and the outputs are similar. Outputs are related to each other. Then we can be sure that the weights will also be similar to each other. So what we can do is we can put a constraint that the weights have to be similar to each other. To put a constraint, we can add a regularizing term, which is something like this in the cost function, that the WA plus W minus WB has to be small as possible. So that is parameter tying. So they're independent, WA and WB, but we are trying to make them similar. But if we force it to be like same, we are saying that they have to be the same, then it's parameter sharing. So this can be used in this is used in CNN, which we'll discuss in future. so for example, if a cat's picture in CNN is shifted by 1 pixel, it's still a cat. So we know that they are both the same. So what we can do is the filter we are applying on the cat to detect a cat can have the same parameters on can share the parameters across these inputs. So that way this can be thought of as parameter sharing. But you have to kind of know the domain to be able to apply parameter sharing. So bagging is bagging is a great method, which so basically it's a method of voting. So you train several different models, and the models vote on the output of the test examples. And either if it's a regression, you average the results, or if it's a classification, you take like the best result. The class for which the most number of models voted for. So if we do an analysis of this bagging, then if we have k different regression models, and they are all they all give an error of epsilon on each example, then and the expected value of epsilon is epsilon square, which is the variance, is v, and the expected value of epsilon I, epsilon j is c. Then the error made by the average prediction of all ensemble methods is going to be this, right? They will take for that data point, epsilon 1, epsilon 2, epsilon 3 will be the different errors from different models. But because we are averaging out the output, the errors will also average out. So this is what will be the average error. But the variance can be proven to be 1 by kv plus k minus 1 divided by kc. Now this is interesting because if they are all decorrelated from each other, so c is 0, so all models are independent, they are looking at different things, then the variance will reduce to 1 by kv. So that's very good, because the generalization error will go up, will go down. And if but if they're all the same, like if you just take one classifier and you replicate it to 100 classifiers and start doing voting or bagging, then the variance will also remain the same. So this will have no effect. So okay, so this is bagging. Bagging is a little different. This is like voting, but bagging is actually used for a specific technique where, given the original data set, you sample with replacement, and then fit different models, same models. So for example, if you are fitting a tree on, you're doing you're sampling, you're given the original data set, you sample with replacement a bunch of data sets, and then you fit a tree on all of them, and then you have the trees vote for the answer. So that's called bagging. That's the actual term for bagging. And in the context of neural networks, though, you don't really need to fit different classifiers, because changes in so you don't really need to construct different classifiers. If you change the hyperparameters, if you change something small, then there is enough difference that so for example, in this one, we are actually training different we are putting a method to get different classifiers, right? We are doing a sampling, trying to set up trees for each of those samples. But here we don't need this extra sample step in neural network. If you change the hyperparameter by a little bit, then the neural network is sufficiently different enough that you can do voting from different neural networks. So let's come to dropout now. So this is the main. This is one of the big things. So go to the notebook and so dropout and dropout. Okay, so how do we use dropout? Dropout, the way we use dropout is that mini batch. Let me explain what mini batch is. What the subset of the data that gets fed concurrently into a neural network. And so let's suppose this is the neural network that we have. Then then what we would do is we would in dropout we would also add we will basically multiply each output by 0 or 1 depending on a mask or a probability. So what happens is, so if you see this normal neural network becomes something like this, and in every mini batch we sample this mu. And mu, so typically hidden unit, there is a 0.5 of mu is has a 0.5 chance of becoming 1 and 0.5 chance of becoming 0. And in the input units, it's 0.8 chance of becoming a 1, 0.2 chance of becoming a 0. And we change this neural network to something like this. And then we sample mu. We sample mu every mini batch. We sample mu, and then we run this. Then we run this whole network and do a backpropagation. So that's dropout. And so it can also be thought of as basically taking out a node arbitrarily, taking out an input arbitrarily in every mini batch. So how does that help? So, but if you think about it, like like this is a small network, but in a large network, then possibilities of mu, if you think mu as a vector, mu h1, mu h2, mu h3, the number of possible values of mu can be exponential, 2 to the power of the number of nodes or inputs. So so this can become unwieldy, but you can get like an unbiased sample by like if you want to get expected value for all mu's, then it's very hard to do because there are too many mu's. If for example this network had 1,000 nodes, then it will be 2 to the power of 1,000 different combinations of mu, so it will be harder. But let's do so another way to look at dropout is that dropout is basically an ensemble. So depending on the choice of mu, there are these many different neural networks that are actually in play. And the problem is that but if you see a lot of times in this picture, y is not connected to x at all. But that won't be the case in a larger network because generally if we are sampling at least one of the layers of each, one node in each layer will at least be active. So generally y will be connected to x1. But if you see, this is leading to a lot of different neural networks or sub neural networks, and we are basically doing a ensemble of these. Now bagging there are certain differences. So in ensemble methods, you do not share parameters, but here the trick is this will, if this is like 1,000 node, then the number of subnetworks will become exponential. But the trick is that we do not. The trick is that we share the parameters, so that way we can keep it in memory. We do not that's the only way we can keep it in memory. One second. One second, I'll be back. Sorry, I have a visitor. So okay, so this is ensemble methods, and so there are certain difference between this ensemble methods and dropout. So so one is that it shares parameters, and the other is that in bagging, each model is trained to convergence. Like each model is trained perfectly, but here each model is probably trained for one step. If there is a 1,000 node network, then it's very unlikely that two of them will ever repeat. Two masks will ever repeat. So so they are probably drop out the um, like every subnetwork gets one step, but because they share parameters, they all get trained. Okay, so inference. So this is the last slide. So inference on in neural networks. So inference is basically how do we once we build this with dropout, build a neural network with dropout. How do we inference? How do we get an inference out of it? So one way could be that we could get all the. So in bagging, how do we get it? We just vote. In dropout, what we could do is we could get the expected value of mu, expected value of py given x with the probability distribution of mu. But this is untractable. This is very hard to compute, and there is no simplifying mechanism. So there is another way that instead of getting the expected value, we get the geometric mean. And if we get the geometric mean, then we can do then there's a good approximation, and the approximation is simply to multiply each node by the weight of each node by mu. So if we just take every node, and let's suppose mu was 0.5, then we multiply the weight by 0.5. and then let the model do the forward pass, and then this will lead to geometric mean of all the py given x. There's more in the book, you can see. And so this there's more about it, like how it's not actually proved for deeper networks, but it's proved for shallower networks, that geometric mean will that multiplying the weights will actually prove the will approximate the geometric mean. So it works well in practice. And so that's dropout, and that is all for today's webcast. So let me show you. So the only big mathematics here is used was Hessian and Costa semi-definite matrices. And yeah, Hessian is very easy to at least intuitively understand. Not so it's like the double derivative uh, of a variable with respect to of a vector with respect to a variable, or a vector with respect to another vector. Here it was a vector with respect to a variable. So so you can no, here it was a scalar with respect to a vector. So so those are, but you can just get enough, like, from each topic. Any other questions? And please feel free to write to us, or on Facebook or anywhere else. And if you have any other questions, or our email is info@datacabinet.systems. Thank you. And we'll have another event on GANs next week. Thanks. Take care. Bye.